Hey, and welcome to the demo for this week, week 4. And this will be the same for HSI 255 and 266, just because we're using transistors coming up soon. And I wanted to do a recap of the code. So we're going to start from scratch. We'll do a wired version, we'll do a LabJack control panel, and then we'll do a full code version. Okay, so on this page, we have the wired version. On the left-hand side, you see a breadboard model where ground and VS are connected to the bottom and top rails. And then we have VS coming into the left side of the push button. And on the right side, there's a blue line going off to a resistor. We'll talk about that in a second. And at the bottom of the push button is a 10K ohm resistor going down to ground. So, quick question, is this a pull-up or a pull-down configuration? If you said pull-down, fantastic. That resistor is pulling the signal low. That little blue wire going off to the transistor setup is essentially will get replaced by one of our channels. But for now, it's getting activated by the button. So when I push the button, you can see in the video on the right, that LED turns on. Now what's happening with the transistor? So that blue line goes into a 470 ohm resistor, which goes into the base of the transistor. And we know that a small current going into the base of a transistor activates the transistor. And in this case, the collector and the emitter on the transistor. So the first pin is the emitter, and we see a black line going down to ground. That's very typical of an NPN. And the collector is on the right-hand side. The collector is going through a 330 ohm resistor and an LED, which goes up to VS. I think in the video I used a larger resistor, but that just makes it dimmer, right? So when that LED turns on, I know that the transistor is turned on. So backtrack a second. The base current activates the transistor, which connects the emitter and collector essentially for our purposes. So the NPN is acting like a switch. The emitter, which is connected to ground, then gets connected to that other side of the resistor. So basically we have VS at the top going through the LED, going through the resistor, and going down to ground, which turns on the LED. The load on a transistor setup does not have to be just an LED. In future, we're going to see different components being added to the collector side of the transistor. For example, a buzzer or a motor or some other device that needs to be current controlled. So on this slide, I want to show how we set up LabJack control panel. So FiO5 is the one connected to the transistor base, and FiO7 we're turning into an input. And we'll follow that out. So FiO5 comes over to the base resistor for the transistor. And then on FiO7, that's going to be connected to the push button. And we're going to test these. So in LJ control panel, if you set this up, you can see FiO5. When you enable it, the light turns on. When you disable it, the light turns off. That's exactly what we want to see. And then for the input, if I push the button, I see the voltage state go up to 2.4 on FiO7, which has turned into AIN7. So you can just see the voltage there. In our code, we're actually going to set it up as a digital input, but I wanted to show you the voltage state here. And you can imagine the digital input would either be 0 or 1. And so we're going to use that in our code. Alrighty, so in your own code, I hope you've been having some practice writing your writer's block at the top. You'll see here is an example of one for this program that you're going to write your own. And in this case, the purpose, you can read through it if you like. We have what is the program doing. So it's interfacing with the LabJack U3. I like to put in the model number just in case you change models in future. And we're going to have a count that waits for 500 milliseconds. As you count through from 0 to 20, you are going to set up your LED to blink based on whether it is even or odd in the count. Okay, so it's going to blink on and off, and a push button, if it's pressed, is going to hold the last state of that LED. So if you press the button when it was off, then it'll stay off. If you press the button when it was on, it'll stay on. And when you release it, it will continue. So that's what I tried to capture in the purpose. And you'll note some major points would be, you're going to say how long the count is, what does it go from and to, what channels are you using, and some important information about how you're going to set it up. In this case, I chose to monitor FiO5 as a digital input. Next up, we have the preprocessor directives, and in this case, they're always the same. We're going to use the same four. I'll probably give these to you on the lab test and in most labs. If you are copy pasting them, you'll never remember what they are, so I recommend that you type them out just so you become more familiar with them. The standard I/O, so you can talk to the I/O pins. The standard lib is so that you can look at the lib file, I believe. Windows is definitely the one for sleep function, and then the LabJack ud.h is obviously the header file for the LabJack, and I hope you've had a chance at this point to look through it. There are hundreds of functions in there, and you'll see a couple of the ones that we're using this semester, which I will go through now. So when we start the int main, in section 1, we're going to set up some variables. These variables are almost always the same at the start, so the LJ_error is our error code. If LJ_Q is anything other than a 0, it's an error. And there's a way to set up an error checker, so you can look up what an error code means, but it is a quick, if you have the printf for LJ_Q and it's something other than 0, then you know that there's a problem. And then the LJ handle is you can think of it like the address or the handshake of the unit that we're using. If you had multiple LabJacks, then each one would have its own LJ_handle. And in this case, we have some ints for the channels, channel 7 and 5. And I also set up a counter to start from 0, a digital output for the last state of the LED, a digital output called output, what we will set up to be pushed to the transistor, and then I have a double or digital input to read the button to see if it's been pressed or not. In section 2, this is where you open the LabJack and reset it. So you open the LabJack the same way every single time. And in this case, we're using the U3 device. So you see that DT U3, that means device type U3. And next to that, you see CT USB, connection type is USB because the U3 is only connected by USB. In double quotations, you see the 1. That's kind of a placeholder because the one next to it is first found. So ignore what the location is. Let's just find the first one on USB. And then we're going to save all that handshaking information into the location of LJ_handle. We save that for the duration of the code. On the next line, where it says ePut, so you're now aware of where the LabJack is located, so you can start using its handle, and you're going to do the I/O type of pin configuration reset, and that allows us to use the AIN and DACs and FIO channels, or the screw terminals. In this case, I added a system pause for the demo because I wanted to bring the screen into play, and I'll show you that in a bit. So we're going to start the counter while it is going from 0 to 20, and assuming that each step is 500 milliseconds, I'm going to assume that it's going to run for how many seconds? Think about that for a second. If you guess 10 seconds, great. So 500 milliseconds, and we've got 20 steps. In section 3 there, you're going to see that I'm using the modulo function. So I want to figure out if the number of the counter is even or odd. And if it is even, then I'm going to set the digital output called output to 1, which is a high state. And if it is odd, then I'm going to set it to 0. And that's just going to essentially turn on and off the base of the transistor. So that's my FIO channel. This is how I'm going to determine what state to put it at. But after that, I have to think about, well, don't I have to read the button? So we'll get there in a second. In section 4, we're going to read the button state. And in this case, we've set up a CH button or channel 7, which you see either is the same. This setup is always the same. So LJ_Q is used 3 times in a row there. You see add request, you see go, and you see get result under section 4. And we call this the add, go, get sequence. So add request, I'm going to tell which LabJack that I want to use, and I need to tell what type of I/O type to use. In this case, I'm setting up channel 7 as a digital input, so I have to get the digital input as a bit. So read from channel 7, go and do it, and then get the result, which I just did, so the get digital bit on channel 7, and save it into the location of my digital input read button variable. Okay, so after we've read the button, what do I do with that information? Well, if the button is pressed, I don't want the output to just blink back and forth, 0, 1, 0, 1. I want to keep the state of the last known red button. So if the button is pressed while the LED was off, then keep the LED off. If the button was pressed while the LED was on, then keep the LED on. So that's what's going to happen in section 5 here. And you see if the digital input read button is less than 1, so in other words, if it hasn't been pressed, so it's still state 0, then I'm going to update the digital output last state to be equal to the digital output of output. So in the previous step, section 3, we're updating the output. And then here, if the button's been pressed, then I'll update the last state. Sorry, if the button has not been pressed, I will update the state. If the button has been pressed, I won't update the state, and I'll keep it like what it was before. So this is a little trick. Go back and read this again. If the button has been pressed, don't change last state. Okay, so now we're going to go to section 6. And in section 6, we are going to set the output channel accordingly. Oops. And to do that, I need to set up another one of those add go situations. Now I don't need to get the result because I'm setting an output. I get the result if I am reading a channel, but I don't need to set the result. I don't need to get the result if it is setting. So let's take a look at this. Add request on the LabJack. The IO type is put digital bit because I am setting the output. I've chosen the channel for the LED, which is FiO5. And you see there the DO last state, that's the digital output last state. So if the last state got updated because the button wasn't pressed, then it'll just blink back and forth. But if the button is pressed, then it'll continue to do what it was doing before. So if it's off, it'll stay off. If it's on, it'll stay on. And you can add as many add requests as you like, but then you have to go and do them. The go statement does them in order. Next step. We have section 7, and I am printing on screen what's going on, just as a, for each counter step, I want to see what is the counter stage, what is the output reading. Sorry, when I say reading, I mean what is the state of output, what is the last state, and the button read, what is that as a value. Okay, so in between each step, we're going to sleep for 500 milliseconds, and don't forget to increase that counter. And then you see the end of the while loop. At the end of the program, after the counter has finished, because we exit the while loop when the counter reaches 20, section 8 says, please pause. Oops. And wait for user input. And you'll see there that I want to reset the output. So regardless of what state the LED is in, I want to put digital bit on the channel LED to 0. And then I have to go and do it. So the go statement is to make sure the add request gets done. You'll see close at the end, which is important for your handling of the LabJack. You want to make sure that you close off your communications to it, and then you're going to return 0. And that's it. So here is a full code example. And now we'll spend a few minutes and look at what happens when you run it. Before you run it, just make sure that the x86 is in place for you guys. Okay. And just checking that you've set up an appropriate C file name and your lib file is in the right place as well. Okay, so let's run it. And I'm just going to drag in the terminal and resize it so you can still see what's going on live in the camera view. So let's engage it. The counter is going to increase. We see the LED blinking. When the button read is high, you can see the LED keeps the state. And it's going to go up to 19. Now it ended when the LED was already off. So let's try it again and end it while the LED is on. We just want to double check, our reset at the end is working. So we'll run it again. Press a key to continue. Starts the counter. There's the blinking. Push the button. Don't push the button. Push the button. Keep the button pressed. And the code ends. And when you click a button to continue, the LED turns off. Okay, I hope you enjoyed this demo today. If you like, you can rewatch it to understand what's going on with the code. We are going to be using the add go get sequence a lot, and we're going to be using it in different ways. So you've seen an example today of the get digital bit and put digital bit. We also have examples for setting up PWM in future, where you have 6 add requests in a row before you click go. And we'll also have like get AI in to read from an AI in channel. Okay, so thank you, and I'll see you soon.